Okay, cool. Yeah, thanks a lot for the invitation. And again, so I'm very excited about meeting all of you guys to discuss about the computer vision, discuss about our work Magma. So in this talk, actually, I will quickly present okay, so what's we have done in the past towards building the multimodal AI agent that can see, talk, and act. So I'm from deep learning group, and I'm now a principal researcher working at MSR deep learning group. So and so I think the first question actually you guys probably will ask is, okay, why multimodal agent, right? So why we needed this kind of multimodal AI agent? Because AI agent need a perception, language understanding, and action, as you can see here. So even in the digital world, actually, people probably go through the web page and use different type of digital tools, etc. So it requires this kind of different type of perception and also language understanding and take action, right? And in the physical world, actually, we also see a lot of use cases like domestic robot help you to clean up the table, or autonomous driving car even is kind of a specialized agent, which can perceive and understand the command and also take actions, right? So in my opinion, I think multimodality is one of the key to build these kind of real world applications. And that's why actually I highly believe multimodal AI agent will be very, very crucial in the next round of AI development. And of course, there are a lot of challenges. How to integrate the vision, language, or even other type of sensory data, and also how to enable the decision making and also planning, etc., to accomplish some high-level goal. So this all of them actually are quite a challenge. So before talking about what's the solution we developed, actually, I want to quickly go through, tell you, okay, where are we now, right? So the roadmap multimodal model actually has been couple years. I would say maybe 5 years to 10 years, right? So, and at the very beginning, actually, people are mainly thinking about, for example, very kind of customized or specialized VQA model or image capturing model. And starting from the appearance of the BERT model, actually 3 to 5 years ago, visual language model are relatively not that popular, but a bunch of work are built on top of BERT pre-training architecture. One of the representative work is WereBERT from my lab mate. So basically, it's trained, okay, the visual language BERT architecture across different type of data, and finally, okay, fine tune it for different downstream tasks. And this could be one of the first version of the foundation model in multimodal domain. And later on, actually, with the come out of the clip from OpenAI, actually, it scaled up the multimodal training to billions of images. If you remember, actually, they use 400 million image text pairs, right, and to train the model. And then, okay, back to thing, okay, so we also built some model by ourselves, like a multimodal foundation model called Florence. And the model size is still relatively small, but it shows strong open vocabulary and zero-shot recognition capability across a wide range of visual domains. So this is really remarkable because before that, actually, we can only see some kind of specialized model to recognize the 1,000 category from ImageNet was 10 category from CFI10, right? So these are very limited capability. But here, actually, we are starting to seeing, okay, very, very capable kind of zero-shot or open vocabulary model. And the most recently, we entered the era of large multimodal model, connecting the multimodal vision foundation like CLIP or other type of vision foundation model like Florence, like CCLIP. Actually, we can achieve very advanced multimodal capability. And now we can have a multimodal chatbot such as GPT-4o or even O3 come out a week ago, and which is pretty capable, right? And it can understand the image and chat with you and reasoning over the image and the text to give you a very kind of decent answer. So have a recap on all of these kind of, different type of pipelines. Actually, we can see, okay, the model size is becoming larger and larger, and the training data is becoming larger and larger. And one thing actually it does not change is that, okay, they're still trying to handle in the multimodal understanding task like image captioning, like visual censoring, and etc. Right? So they still lack the ability to interact with word in a human-like manner. One of the reasons is that, okay, they cannot directly interact with word because all of the input sensory data actually are captured by different sensor and then detached between the environment and the larger foundation model. And after the training, actually, the model actually just, okay, off the ship, offline, take different type of image as input, and then, okay, there is still inability to interact with the real world environment. So that's really, really a missed component for all of these existing multimodal language model, all of these kind of multimodal foundation model. Yeah. So talking about multimodal AI agent. So is AI agent only obviously actually it's an emerging topic and it's very broad concept. I want to narrow it down to the multimodal AI agent, not just okay, a very broad AI agent. So in that sense, multimodal AI agent is more like, okay, you need to have a multimodal understanding capability or multimodal perception capability. And in the meanwhile, you have to have this kind of multimodal action prediction and action taking capability. So these two actually should be cooperate with each other and also driven by a goal. So it should be a goal driven. It's not just random, okay, wander in the environment, right? So it should be driven by goal. And if we unfold this, you can see, okay, it's basically a chain of um, perceive and take action, perceive and take action. And also it's needed to be driven by a goal. And this goal actually usually can be represented, can be conveyed by language. So that's why I think multimodal AI agent should be definitely able to see, talk, and act simultaneously. And I will quickly go through the path or even my personal path towards this kind of multimodal AI agent. So that, okay, all of us are on the same page and see the challenges and see the opportunities moving forward. So I will quickly go through the three pieces of this, in this talk. So the first part is how we build the multimodal vision foundation, which is the foundation for this multimodal agent, and how we connect the multimodal vision foundation with language model, which is definitely a very kind of necessary component to further push forward the multimodal agentic model. So the landscape of vision task, I'm sure you guys are also much, much more familiar with this, landscape. So the vision task is quite, heterogeneous. So there are a lot of kind of dimensions, including the modality of input, including the granularity, including the dimension, spatial temporal dimension. So that being said, okay, so for myself, for many of the, researchers in the vision community, actually, we have been spend a lot of effort to handle a customized or a specific task and then optimize that specific task for a long time. So this is not very good because this is not like a language model, right? Which can handle so many different type of tasks with a single black box, right? So this is very different. That's why we have been thinking of, okay, whether we should build some kind of more capable and a more kind of seamless kind of model architecture. So that's why actually we wanted to build the multimodal vision foundation. I will not go through all of this work. I just give you some high-level idea regarding this effort. So we needed some kind of beta vision encoder, which should be very, very discriminative, but in the meanwhile should be very semantic rich. So that, okay, we can use language as a common interface to share across different visual information across different domains. And this will also bring some unique benefit in terms of zero-shot transfer to novel visual concept and domains. And in the meanwhile, given the complexity of different type of vision tasks at different granularity level, we do need to somehow to build some unified encoder decoder, right? So that we can really, okay, put all of these different tasks into the same interface. So this is what have done in the language domain, but so barely done in the vision domain, but we are striving for that as well. So I just briefly introduce a simple idea we developed back to 2022, which was one of the core components of the project Florence back to 2022 at Microsoft. So the idea is pretty simple. So this idea is essentially trying to bridge the gap in between the image classification data and the image test path. The image classification task is basically trying to map the image to discrete label, right? And the image text pair contrastive actually is trying to align the image text pairs and push closer for the positive pair and push far away for the negative pairs. But here actually we unify these two type of data into the same interface at a single point, as you can see here in this kind of 3D space. So we can essentially leverage these two type of data seamlessly and also achieve the best of both worlds to achieve very good kind of discriminative representations for image classification for image input, but also very broad semantic coverage for open world scenarios. So the idea is pretty simple. So we just build the affinity matrix, but also assign some positive entries for the off-diagonal entries in this affinity matrix, given that there's multi-to-multi correspondence from the image classification data. And finally, we do a very, very manual change to the original kind of contrast loss. And finally, you can see, we just use a single contrast loss to merge these two type of data and get very good representations. So, which is pretty semantically rich, as you can see from the left side. It can really help you to merge the similar semantic concept into the similar location in the feature space. And in the meanwhile, it's become more and more discriminative because it can absorb the knowledge from the image classification data. It can help you to distinguish the fine-grained kind of species, even though this is out of domain. So this idea was leveraged by Project Florence as a core algorithm, and we finally achieved very good performance and beat the clip across 44 vision benchmarks span from zero-shot image classification and image text retrieval, object detection, etc. So this is a very simple idea, and this could be one of the very first efforts that we built towards this kind of multimodal vision foundation, not just closed set vision classification or vision recognition system. So that's why we expand this kind of image level multimodal vision foundation to region level. We developed GLIP, which is also another inferential work we built, and it's essentially help you to associate the phrase in the language description and the regions in the image. So this kind of open up very great opportunity for people to, do this kind of fine-grained kind of reference, kind of in expression reference. So this is really remarkable kind of capability. And later on, we expand it to GroundingDINO. I'm sure you guys know this work, probably even used it in your practice. So GroundingDINO actually is a very natural extension of GLIP by replacing the dynamic height we used in GLIP with the DINO, which is much more powerful object detection architecture compared with GLIP. By the way, so if you have any question, please interrupt me anytime. And then, GLIP model was extended to GroundingDINO, and then further, this GroundingDINO can be combined with SAM and the GLIP for different type of use cases. So we further expand it to the pixel level by developing the segment everything everywhere wide advanced model. So it can support not only just text prompt, it can also support the spatial prompt or image or visual prompt. So this can significantly open up the interactive capability for any of this kind of multimodal vision foundation so that it can support different use cases. So you can see here, so gradually we are seeing more and more kind of converged computer vision model or multimodal vision architecture. And so it has the ability to support different type prompt. It has the ability to produce different output. But so the capability of all of this multimodal vision foundation are still not very, very kind of satisfactory in terms of interacting with the human, in terms of digesting the human intent through the composition. Back to 2023, with the emergence of the large language model, we see the sparks of AGI in multimodal model, especially in the GPT-4V, right? On the right side, if you look at this image, so I personally, I was quite shocked by the intelligence shown in the composition about this image. So it's quite impressive, I would say. And we, as a team, actually back to 2023, actually my colleague actually developed the Lava, which can somehow largely mimic this behavior shown in GPT-4V, and is showing very great kind of composition capability with Lava pipeline, which is much smaller, which is very cheap to train. So a typical large multimodal model is something like this. So you can see here, people usually, okay, try multi-stage training and then, okay, do some kind of alignment first and then, okay, some instruction tuning and now probably some IR training on top in the most recent literatures. So we developed 5-3 vision. So as a company-wide effort, actually, Faster Vision is first multimodal model in the 5-3 family. It's very, very small. It's just 4 billion parameters, and has very strong OCR or text VQA, etc. Capability. And the design choice is very simple, and we just simply follow Lava 1.6 and adding some linear separators and do some pixel shuffle, right? So the capability is very strong, as you can see from this figure. So overall, you can see here, so we have some very strong multimodal vision foundation model and connect with the large language model and spent reasonably kind of, good effort to make it work for, yeah, for the multimodal composition, etc. So now, okay, I want to talk about so how we are, we approach into the multimodal agentic model. So why I'm playing with a multimodal language model, including Lava, GP4V, and Fast Vision, I have been facing a problem for this model to ground on the visual content, which can be easily obtained by GroundingDINO, Glib, Sim, etc. And there is no easy way to achieve this except for fine-tuned model to detect and grounding. But unfortunately, we cannot fine-tune GP4V. But GP4V has a very strong reasoning or composition capability. So that's why actually I played with the GP4V and finally figured out a very simple way, which is called set mark prompting. Just simply overlay the visual marks on the image. It can immediately elicit the grounding capability and the more important character response. If you look at the left figure and the right figure, right? So it has the ability to answer the question correctly and also grant the answer with the visual marks in the images. So this is really, really mind-blowing why I first saw this kind of property. And it can even be used to help you to, uh, write a very kind of detailed instruction to use a tool represented or conveyed by the visual input, right? So this is very, very interesting. And the set mark actually for large multimodal model has been heavily leveraged or used in different tasks and different domains. So you can see here, it can be used in UI navigation, it can be used in robotics, it can be used in common domain. Nowadays, actually, it can be even used for the image editing, measurement. So how is the quality of the image generation compared with the, for example, the target image? So some fine-grained kind of image quality measurement. This is also very interesting to see. So there are a lot of use cases like UI navigation. After one week after the release of Santa Mark, actually some undergrad students from MIT already built some UI navigation. So I would say a lot of follow-up work have very similar setup to this demo, which was built back to 2023 November, if I remember correctly. So a bunch of work, including ourselves, actually got inspired by this, and then we built some zero-shot smartphone GUI navigation based on GP4V and Setmark on the different type of techniques. And another benchmark, which is Visual Verb Arena, also built on top of this technique, and then evaluate the GP4V or GP4O recently for this UI navigation. Of course, for robotic manipulation, so different type of robotics manipulation task use this type of visual grounding capability by prompting GB4V to accomplish some navigation and the manipulation task, right? So that being said, okay, so we are seeing the dawn, we are in the dawn of the multimodal AI agent, not only in the digital world for different type of UI navigation, web navigation across different system or OS. And in the meanwhile, actually, we are seeing the vision language action model, which is essentially a multimodal AI agent that have been developed in the physical world for control different robot systems for navigation, for planning, and for manipulation, etc. So we are seeing a lot of works. And personally, in our team, actually, we also have a number of research effort falling into these domains. We develop Omniparser. Probably you guys know this work to improve the visual grounding for multimodal language model and exact to leverage the Monte Carlo tree search and the exploratory learning to improve the planning capability for web navigation. And in the physical world, actually, we have developed the Transfer A and improved the spatial temporal awareness for robot policy. So this is very, very interesting work, but both of them actually are only used or applied for the digital world, either digital world and the physical world. So if you trace back a bunch of work, okay, I explore different type of action model or agentic model for separate domain, but I have been think of whether AI system should be split or should be isolated into the digital world and the physical world. In my opinion, I think this is not the case because as human, we can essentially traverse across digital world and the physical world and accomplish some task in either of these domains or even a hybrid of these two domains, right? So that being said, I really want to build some model that which is a single foundation model for both digital world and the physical world, and can we build a single foundation model for both multimodal understanding and action prediction? Because we previous model actually usually fine-tune the multimodal model to support the action prediction for UI or for robotics, but it can not again, do this kind of regular multimodal vision understanding, multimodal QA, because it was overfit to the specific domain. And we do not want to do that. We really want to build a foundation and how to induce the both verbal and the spatial intelligence for the model, and how do we scale up for our agentic pre-training. One of these questions actually are quite challenging and quite new. Back to 1 year, roughly 1 year ago, less than 1 year, June, July, last year. And that's why actually I built the Magma model, which is a foundation model for multimodal AI agent. So if you look at this, so we really have a very big picture regarding the capability of this multimodal agentic foundation. It's not only about the multimodal action prediction, it's also about multimodal understanding from left side, and it's also about the multimodal action grounding and the planning and in the middle. And finally, it's also about the multimodal agentic task to accomplish a chain of action prediction to accomplish some agentic task, right? So we are trying to really build a foundation. Even it's just a baby step. Actually, I would say this is one of the first work which can help, which can be used for either the digital world and the physical world or across the border. So this is very interesting project and a very interesting kind of outcome we have achieved through the Magma model. And so you know that Cetamark is very popular for both UI navigation and the robotics manipulation. And as an author of the Cetamark, actually, I draw the inspiration from the community to extend the Cetamark into the pre-training pipeline. So we apply the Cetamark for both UI navigation and the robotics manipulation, and ask the model to select the mark to which we need to control to finish the task. It could be the UI navigation task, it could be a robotics manipulation task. So you can see this can significantly reduce the search space and also improve the action grounding capability for the agentic model. So, and also there's no, domain gap in between these two because we are unify this action grounding into the same interface. Just simply ask the model to select which mark to control, right? Which mark to move, something like that. In the meanwhile, we do not agentic task is a temporal, is a kind of it consists of multiple temporal steps. It's not just a static grounding problem. So that's why actually we further extended the set mark for action grounding to the tracer mark for action planning. So we are not only asking the model to localize the mark to move, but also asking the model to predict, how to move this mark and for the agentic task, right? So this kind of trace mark actually forces the model to learn the long horizon by predicting the distant future action represented by the trajectory. Even though this trajectory is approximated format of the action, of the real action, but it can provide very, very effective way to leverage the unlabeled video data and also make the model plan ahead roughly. So this is what we think, okay, tracer mark could work for this Magma model pre-training. And based on this, we finally, okay, look into what kind of video data we can use. So actually, we can use a bunch of video data. So in my opinion, as a motion in the video actually are not fully leveraged or exploited in previous work. But here actually, my intuition is that, okay, motion a great action supervision. It persists properly. If you look at these different type of videos, right? We extracted the trajectory for the point, for the grid point based on the tracker. Of course, you can choose any other more even advanced kind of point track system to extract one of the trajectory for different point. But here, I want to give you a sense like, okay, so this motion, many of these motion capture the action in the 2D space, in the 2D spatial temporal space of the end effector. It could be the human hands, it could be the moving object, it could be the end effector of the robot, right? So all of them actually are pretty useful, but we cannot directly use them because all of them actually also come with a lot of noises. So that's why we propose an algorithm, persistent algorithm, to essentially extract the useful trace of mark information for the videos. So this is pretty interesting for us, and we spent roughly 1 month to figure out the best way to convert the raw kind of motion signals into some, useful and informative motion of the end effector here, which is here the human hand, right? So to accomplish some task. So this is very, very interesting kind of extension of the original point tracking system, because point tracking is just give you some trajectory, but in the end, actually, we do not, a agentic system just do not need to, give you the point trace, something like that. The point trace, on the other hand, actually will be very useful to really, okay, induce some capability for the multimodal agentic model. So this is what we thought while we developed the Magma model. And in the end, so the whole pipeline is pretty simple. And we just simply merge a bunch of data, instruction videos, robotic manipulation data, OpenX environment, and UI navigation data, and the multimodal understanding data. All of them actually come with some sort of set mark and trace mark. And essentially, okay, set mark can enable the unified action grounding across different modality input, and also the trace mark is applied to video and the robotics data to enable the action planning capability. So finally, the architecture is pretty simple. There's nothing fancy here, I would say. It's just regular plan multimodal language model architecture as shown in earlier slide. And it's just simply take different type of input. It could be natural image, instructional video, UI navigation, robot manipulation. And finally, it will decode different type of output. It could be a verbal output, answer your question, right? It could be the spatial information, some 2D coordinate or 2D coordinate sequence for different type of input. And finally, some of them actually come with some action prediction. It could be the 2D point plus some action tag. It could be the 7DOF for the robot arm. So that's it. So it's based on the complex extra large because it can take actual resolution input, and it can the language model is just simply the Lava 3 8 billion. Back then it was a state-of-the-art, but now probably there are more kind of advanced language model backbone. So we train the model and then we evaluate it. So nothing fancy here. So we just briefly evaluate the model across different domains, multimodal understanding, UI navigation, and robotics manipulation in this short manner. So we do not fine tune for any specific task, but you can see here across the board, actually, the Magma model actually is essentially doing good job across the whole different tasks. So which essentially, okay, prove our concept that, okay, so we probably do not need to develop individual model or pre-train individual model for different digital world and the physical world task. We can essentially unify this training into the same interface, and then, okay, get a single foundation model for different type of tasks, because essentially this agentic model or agentic task actually are just a combination of verbal intelligence and spatial intelligence. Yeah. So we fine tune, of course, some model in the real world kind of task. We collect our own real robot trajectory and fine tune Magma model in this real robot trajectory, and compared with OpenVIA. It can significantly outperform the OpenVIA across some tasks, especially some tasks which require this strong spatial understanding or spatial reasoning. And on the right hand, actually, we also did a little bit of very efficient fine-tuning, maybe just take 1 or 2 hours on Multimodal, and then it can achieve very good performance as well. So the spatial understanding of the Magma actually is a key. So that's why actually we also quantitatively evaluate the spatial reasoning capability across different different benchmark, and also have some kind of zero-shot test case on the right side. So we also apply this model for video QA because we really want to build a model not only just give you some action, because sometimes actually the interaction between human and the AI, the agentic model is not necessarily always ask the model to take actions. It could be also a conversation, right, across different domains on different type of input. So that's why actually we at the very beginning we designed the model to be able to do the video query as well. Take some video input and answer your question, and probably you can even prompt the model to take actions while you have the conversation, while you interact with the model. So this is what we think is very important. So we built some demo. I'm sure you probably was already saw this demo on our project page, and it could be able to help you to book your flight and check your weather, etc. And this is not new anymore because we are seeing a lot of demo like this. But I want to mention that, okay, this is a model with only 8 billion parameters, and it can run locally. It's not necessary to call any GPT-4V or GPT-4 API. And again, okay, this model is applied to the real robot control. So this is not in simulator. This is a real robot. So I want to especially draw your attention to the left example. So I'm sure you never saw such kind of example. Okay, putting this sausage in a very kind of narrow space, on the yellow object, right? So this require very frequent spatial understanding and spatial temporal understanding to make it work. So it's not like I put some object in the very kind of bigger, very big bowl, something like that, right? So it's really require very precise spatial understanding and spatial reasoning. So on the right side, actually, it can generalize to unseen task, push from left to right, even though okay, the model was never trained to push this close from left to right. It was only trained from for the pushing from the close from right to left in the training data. So yeah, and we apply this for egocentric video because our model was trained on a bunch of egocentric video, and it have very good kind of action planning capability. That's why actually we can transfer this action plan capability to the verbal space to describe or to instruct the user how to do next and what to do next to accomplish some task. So this is very interesting and very useful application for this kind of VR or AR type of thing, I guess. So I will skip here, and then okay, another interesting demo we built is okay. So we directly pull the Magma model from our Hugging Face and then okay, apply this model to run a game. So collect the green blocks by controlling the robot. So sorry, you can see here. So it's quite interesting. What happened? So why it cannot? Interesting. Okay. Anyway, so it cannot run, but you can see this demo in our project page as well. So essentially, it's required very strong kind of spatial understanding and spatial reasoning capability, and also needed to understand the visual input very well. So I think the Lava One Vision or GB4O Mini, both of them actually failed very badly for this task. But Magma actually, in this short manner, actually can work very well, even though we never trained this model on this type of input, never. Yeah. So I want to conclude with these slides. So Magma showing a lot of exciting capability. Probably it's showing some very interesting applications, but actually it does not have a lot of essential capability like reasoning capability, like planning capability. I want to especially highlight the planning capability. So Magma can accomplish some atomic action or its atomic tasks, like okay, push the close from left to right. But this probably is just a very, very minor and a narrow subtask. in a very high level task like cleaning up the table, right? So we really want to build a model that can crack this high level task, clean up this table into multiple subtasks, and then okay, accomplish each of the subtasks progressively, and probably even have some self verification or self checking mechanism to verify whether whether thus far actually the past step past subtask actually have been already accomplished or not. So it's really essential for us to really lift this model to up to the next level. So I would say Magma is just a baby step. It's really kind of preliminary, and is still far away from a very kind of intelligent multimodal AI agent. So in that sense, I want to highlight that, okay, multimodal AI agent really need more. So it's not only about the verbal intelligence, because in the language space, actually, we have a very strong reasoning model, but this reasoning is not grounded on the visual observation on the digital world, on the physical world, like what human are behaving, right? So that's why actually we need the multimodal intelligence. But multimodal intelligence essentially is just connecting the visual input, and visual observation, and the language space. So it's still not enough. So in the end, we really want to have some abstract kind of spatial and temporal intelligence, which can enable the model to capture the position, capture location, capture dynamics of the object, and interact with the 2D and the 3D world along the temporal axis. So this type of intelligence actually still largely missed in most of the multimodal vision foundation, but which are very essential. It could be, very kind of important to really open up the application of the multimodal AI agent. So if we summarize this into a pipeline, so you can see here. So a multimodal AI agent really need to be able to understand and to do the reasoning. And this reasoning could be the low-level reasoning or high-level reasoning for the planning, right? And then, okay, do the action grounding. So you need to ground, okay, this action into the raw signals, into, your end effectors, etc. And finally, okay, produce some very reasonable and very kind of decent action, which can be applied to the real system or real tool, right? And it's a loop. So basically, right? So finally, actually, I want to revisit this O3 released by OpenAI, sync with images. And interestingly, they also have a sentence like, okay, visual reasoning in action, right? So you can imagine this type of simple, image crop, image zoom in is just a very simple action in the image domain. So it's very preliminary. It does not involve any kind of consequent kind of action taken and consequent kind of
Sorry, your
observation. So
last speaker might not have time to
yeah.
go.
Oh, sorry.
Yeah,
So
it's going to
yeah,
jump.
so this is my last slide. So I want to use Magma model on Magma work actually to really draw attention to the community that okay, we really want to bring the AI brain out of weight. And yeah, thanks a lot for your attention. And yeah, I would like to discuss offline or even okay follow up later about this work and about future collaboration, etc. Yeah, thanks a lot for your invitation. Yeah.